Hello everyone, my name is Lewis Leonard and I'm an application engineer at Rigel Medical. Firstly, I'd like to thank you all for attending this webinar today on the latest version of NFPA 99 2021. Now this is an introduction to electrical safety, so we will start with the fundamentals of electrical safety, and then as we progress we'll get into NFPA 99 tests in more detail and also to highlight any changes you may not be aware of. We have developed this to not only simplify testing, but also to go over some of the real life techniques when it comes to unconventional types of medical devices, such as those with no exposed conductive parts or ultrasound devices. And hopefully this will help clear up any confusion when it comes to testing. Now, if you've got any queries on these types of tests, if there's any queries you've got at all, just save them for the end of the presentation, and I'll go through these individually. Now, these slides are available in the handout section below in PDF format. If that's not available to you, just send a message as well, and I will get those sent over to you via email using the registration form. There has been a slight change, so my colleague now is going to do the demo with the 2.8 Plus, colleague James, and he will go through the automatic and manual modes of the 2.8 and some of the data transfer protocols. So firstly, a little bit about ourselves at Rigel Medical. We are renowned globally as a designer and manufacturer of reliable, portable and compact biomedical test equipment. Our products ensure that critical medical equipment is safe to use throughout the device's life cycle, and as metrology specialists for almost 4 decades, our innovative testing solutions have been mitigating risk worldwide in healthcare organisations. So we've got 2 operating locations. Our main manufacturing site is based in County Durham in the UK, but we've also got an office in the USA, that's in Tampa, Florida, which is headed up by Sean Daly. But we are a global company. We've got 7 global authorised service centres. We're operating in over 110 countries through our 40 plus distribution partners. Okay, so starting from the beginning, where electrical safety was implemented, where the risks from medical devices occur for patients. So when an individual comes into contact with any type of faulty electrical equipment, there is always a potential risk for electric shock. The cardiac functions, the nervous systems, the muscular systems, they're all sensitive to the effects of electrical current passing through the body. And this is especially true at the commercial frequencies of electricity, 50 or 60 hertz worldwide. Now, there is a further substantial risk from electrocution in healthcare environments due to the direct patient contact with medical electrical equipment. The human body is composed of water, ions and minerals, and it's a good conductor of electrical currents. More than 99% of the human's body resistance is by the skin, and that's why it's considered a really good barrier to electricity. Unless, of course, it's wet, then that resistance is reduced. The problem with medical devices is they're often connected close to the heart, and also they may be bypassing this effective skin barrier with its high resistance. Couple that with the sensitivity of tiny currents for cardiac muscles, then these increases the risk significantly in healthcare organisations and facilities. Patients are also often in poor health, they're anaesthetised or unconscious, and they may be possibly unaware of any electric shock occurring. Now, during serious operative procedures or recoveries in CCUs, a patient is then even more vulnerable to these electric shocks. So there's all types of factors going on when it comes to electrical safety in healthcare environments that make the risk substantially more increased than it would be around the home or in industry. And it all comes back to Ralph Nader's most shocking expose that revealed that over 1,200 Americans were electrocuted annually during routine procedures. Now, with this being back in 1971, most of you are probably already aware of this expose. It comes up time and time again. The risk is obviously greatly reduced in the modern world because medical devices have thankfully greatly improved in their safety, but the risk is still there. The microshock threats are real and they do exist. So it resulted originally from an increase in the use of cardiac catheterization procedures and external pacemakers with open heart surgery. And this is where relatively minor electric shocks can lead to ventricular fibrillation, or VF. So the outcome of this debate led to the growth of a whole new sector of technical support for the users of medical devices in healthcare. So the safety standard IEC 60601 or ANSI 60601 was formed, and parts of this have still survived to this day. Thankfully, these revisions of electrical safety standards have led to massive reductions in death from both macro shock and micro shock. So, in theory, the whole biomed, BMET sector is derived from this expose from electrical safety and testing of those devices, and things have just snowballed from there. The sector has just grown and grown from this original outcome. Now we're going to talk a little bit about electrical parameters. So this is an introduction, so we are going to go through some of the basics just as a real refresher. So voltage is measured in volts. It's the potential difference creating the electrical pressure driving current around a circuit. There's current, which is measured in amps. This is the flow of electric charge or electrons in a conductive circuit, or carried by ions in electrolytes through bodily tissue. Resistance R is measured in ohms, and this reduces the flow of current in a conductive circuit. The image on the right, this shows Ohm's law, where voltage equals current times resistance, and also the electrical potential, which is the energy per unit charge between 2 points in an electric field. So the electrical potential is always location dependent. I appreciate this is the real basics, but we like to start here and just progress as we move through towards electrical safety. There's a few more important electrical parameters to understand, which are certainly relevant to electrical safety. There's capacitance C, which is measured in farads. This is the storage of electrical energy in an electric field. AC voltages are stored and discharged. These AC currents will flow. DC voltages are charged and stored. DC currents will not flow. Now, AC is highlighted as this shows how electrons can flow to the casing or the applied parts or patient leads of medical electrical equipment. Then we've got ground or earth. This is the 0 volts, point of reference, and it provides a path for electrons to flow in the case of faults and leakage currents. Frequency F, which is measured in radians, hertz, or hertz. This is the number of cycles or radians per second. So macro shock occurs when current passes through the body via contact with the skin. And this aspect will apply to all types of electrical safety, no matter where you are. Fortunately, external skin, when it's dry, has high resistance, and this limits any current flow through the body. One thing I didn't highlight from the first slide is that many medical procedures involve moistening the skin, and that will lower the resistance significantly. This could be ultrasound gel, surgical applicants, and patients are often in contact with medical electrical equipment with these surgical applicants, whether that's indirectly or directly. And this study here shows the perception, or the physiological effect of currents at different levels. So at a commercial frequency of 60 or 50 hertz, these are the levels you'd expect the different physiological effects. Ventricular fibrillation, to 3 seconds of 100 milliamps is going to occur at this commercial frequency. Now, patients in medical environments are susceptible. They're uniquely vulnerable to this risk. And microshocks occur when invasive patient connections are placed across or in close proximity to myocardial tissue or nerves and the heart. And because the components in the blood have very low resistance, small levels of electrical current can induce cardiac arrest from ventricular fibrillation. We can see from the previous slide, ventricular fibrillation occurred at 100 milliamps, 50 to 60 hertz. Now this is for the commercial frequencies as well. It doesn't highlight that. It's much lower. An increased risk of microshock can occur as low as 20 microamps, where it can lead to death. So you're talking about a very low level of current, effectively 5,000 times less than that of macro shock. So there's a huge disparity there. So now we've got the frequency response of the body. So the human body is about 1 to 2 kiloohms. The effects of current at 50 or 60 hertz, there are no discernible differences. The effects of electric shock pretty much the same at these frequencies. As the current frequency increases, the body becomes less stimulated, which is why devices such as diathermies that are using very high frequency current, it's not going to induce ventricular fibrillation to the patient. Now, this is important when you're looking at the procedure for measuring leakage currents, because what the circuit does is replicate the human body for its frequency response and its resistance. So you're trying to replicate or simulate the human body, the actual currents that are perceived by the human body, and that's why it's recommended in the NFPA 99 code, in the standards, and you'll find there also obviously in your safety analyzers. So electrical safety testing, we know it's important, and it's a practice that should not be compromised. It just guarantees the safeguarding of clinicians, patients, and any visitors. The primary process is to prevent any patient or operator being exposed to currents that are not part of the functional operation of the device. These currents you will know as leakage currents, and I'll elaborate a little bit more on that in this section. So there are several specified mandatory barriers within the circuitry of medical devices to guarantee that leakage currents are non-hazardous. One of the main ones is a grounded connection. Now this is not true for all devices, this is only for class 1 devices, and it relies on a protective earth which provides a very low resistance earth path for leakage currents to flow to ground if anyone was to come in contact with exposed conductive parts. So if a fault was to occur and there was a large current on the enclosure, it will follow that easy secondary earth path back to ground rather than through the patient or the user. On top of this, the surge in current down the earth or ground will be detected by RCDs, protective fuses, which will interrupt the voltage supply. We've also got insulation. There's basic, which provides sufficient dielectric strength, supplementary, which is an additional second layer, and it's class 2 devices that use this supplementary protection, so there's no earth connection required. The barrier is provided by that double layer of insulation. So why is safety testing important? The objective is to test for breakdown or damage to confirm the medical equipment is safe to use. Now, as time moves on, medical devices are becoming safer and safer, and failures are becoming less evident. However, performing these tests does protect against any macro shock or micro shock when faults occur with a medical device. It prevents legal liability, it protects patients, staff and visitors, and it's done at various stages of the product's life cycle. So it's done at acceptance. Most medical equipment is widely designed and developed in accordance to 60601 safety standards, and that sets for strict rules on the design of medical equipment. Now we know that the primary safety process is just to prevent any patient or operator being exposed to those currents, whether that's with a supplementary protection, whether that's through class 1 grounding. There's lots of ways to prevent any leakage currents reaching the patient or user. We've also got PMs and post-repair. So safety tests and regular maintenance carried out by end users in healthcare facilities help to detect any potential defects that have happened either through general use or when the device has been repaired and it's been opened up, any parts have been replaced, so it can help identify any risks. Because in some cases, the repair could have been done with a fraudulent part that's somehow slipped through the net. Obviously, these cases are very rare, but it does happen. And if this occurs, electrical safety tests, any visual checks and performance tests will likely detect any of these problems. So protective grounding provides a current path in case of any leakage or fault currents. Now, many class 1 devices will have multiple exposed conductive parts or connections. A couple of good examples are patient beds and sterilization baths. There will be multiple parts on there that a patient could touch, whereas if a current was present, an unsafe current, then there's a risk from electrocution. What earth bonding does is prove the protective integrity from touchable conductive parts of the medical equipment to ground. So over a relatively short period of time, connections or bonds can fail, and that leads to an increase in contact resistance. It's particularly true in the high workload, high stress medical environments. Now visual checks will provide some safeguarding against this, but poor contacts might be imperceptible. So we need to carry out these tests during our PMs, our post procedures and acceptance. And we're measuring the resistance between exposed connections and the protective ground. The lower the level, the better, but the limits are stated depending on which standard you're using. So in NFPA 99, it's 500 milliohms. That's the maximum allowable limit. Insulation, not a mandatory part of testing, certainly not in NFPA 99 or many of the other types of or many of the other standards and codes, although it is in the Australian version, most standards, that's not the case. Now here a high resistance is more beneficial because you're measuring the isolation between the conductive parts of the circuit and the enclosure. Now our devices have different voltage ranges, and that's to test non-standard voltages, so anything that's got safety extra low voltage equipment, DC power supplies, etc., has got that option to test at lower voltages. Now what is leakage current? It's any current that is non-functional according to 60601. It's unavoidable, and it's easily overlooked and subject to incorrect testing. So all mains powered equipment is developed to only ensure safe levels of leakage current are achieved. not completely eliminated. You can never completely get rid of leakage current. It's always going to occur due to capacitive coupling. But during development of these medical devices, the high levels of isolation from any electrical potentials to any accessible conductive parts is a big requirement for the medical device manufacturers. And the standards do have rigorous statements that say that the device must have certain levels of isolation, degrees of spacing, and that just ensures that leakage limits are as low as possible. Now, earth and enclosure, apologies, I call it earth and enclosure. Obviously we're talking about NFPA 99, and it's more specific to the USA, so ground and chassis might be a more applicable term. So if I use the term earth, I might mean ground. It's just the terms that I'm used to using. The earth and enclosure type, the ground and enclosure type leakage currents have limits that reflect the values of macro shock. So the risk to the user or clinician, the visitor, the risk there, the limits are higher because it's from the previous slides, macro shock had higher levels of current before ventricular fibrillation occurs. Now, from the micro shock slide, we know that medical electrical equipment is designed to have high levels of isolation due to applied parts and the risks of micro shock. And that's why the limits for the applied parts are much lower and there's higher degrees of isolation. Stray capacitance. Class 1 earth leakage travels down the earth path, ground path to earth within a medical device. In a standard TN system, current in the live or hot wire carries both the functional current and the leakage current, whereas a neutral wire only contains the functional current. Earth leakage can actually be expressed as the live current or hot current minus the neutral current. So how does that work? So from one of the first slides, we talked about how AC currents flow in a capacitor. The animation shows how capacitive currents flow to the enclosure from any internal components. In safe to use equipment, there is always a small leakage current flowing to earth. The current's only a few microamps, then it's not hazardous. The earth connection is there to keep the user or patient safe in the event of a fault whereby substantial levels of current flow from the circuit occurs from the enclosure or the applied part. So it allows that current to flow down the earth path and not through the patient. So in a different standard, 62353, the live current minus the neutral current is actually one way of determining leakage current. So there's that imbalance between the two conductors is measured, and that gives you the total leakage. So that's one way of actually measuring that type of current. But in NFPA 99, it does specify the configuration of mains for electrical safety test. So leakage is always measured the conventional way, and that's by having a body model in line with the earth conductor or the enclosure or the applied parts, and it's measuring that current directly. So NFPA 99 is always measuring it directly, which is the most accurate form of leakage measurement. And it does specify the configuration of the mains for electrical safety tests. A terra-neutral system. This means that the neutral is at the same potential as ground. In the USA, 120 volts through the hot conductor. Leakage current is typically measured from a high potential to ground, not from the hot to neutral. This is where the functional current is according to some standards. And this ensures the highest possible leakage is measured. Now on a non-TN system, the highest potential from phase to earth is not achieved because leakage, due to the leakage currents, are limited to isolation levels of the supply system. So no valid leakage measurements are possible unless the safety analyzer is able to produce an internal ground at half the line voltage. Now, this is actually stated in NFPA 99 in one section. You might have already seen it, where it states that an adapter can be used temporarily to produce an internal ground. And this allows you to perform a test if you are carrying out a test in situ on the IT system. Now, our devices have an IT system detection and notification, which is a useful feature as it lets you know if you're on the wrong type of system. I'd ignore the values from this slide. This is from our UK-based presentation. It says 230 volt, so that should be 120 volt, and then we use an arbitrary value for half the line voltage. So 70 volts would be a good example, just to be aware that the values might not be true to the voltages that you're used to. Just using an example. So the secondary ground path is a common problem, but often unnoticed. It occurs when medical equipment is connected to other equipment. This could be data lines, monitors, endoscopy, or water. We know that current takes the path of least resistance, and the image represents an example of a secondary ground connection via a data cable on a PC. Most of the current is taking the path of least resistance rather than through the measurement of the safety analyzer. So the safety analyzer uses a body model, which is typically 1 kilo ohm. It's going to follow that easy path back to earth or back to ground via the data lines. This results in significantly less current flowing through the analyzer, which is potentially dangerous because hazardous equipment could pass the leakage test. Now, if you look at the example in the image, compared to the 1 kilo ohm resistance of the body model, the secondary ground path here is just an arbitrary value of 1 ohm, which is a typical value you're going to measure. Values are much less than can be expected via an alternative earth. So that means you could be getting a 1,000 times error or more. Again, our safety analyzers do have a warning if a secondary earth path is detected. Input protection classification. You've seen these symbols before. Class 1, which is relying on the fault currents to ground, and Class 2, which is double insulated. Protection is relying on additional insulation. So a symbol on the left, Class 1, and on the right, Class 2. These are typically found on the rear of the instrument, close to the power supply. As experienced biomed, you can be well aware of these types of symbols that are available to you. Sometimes they're slightly different. You might have an equipotential symbol there, but they all effectively mean the same thing. To carry out an electrical safety test, normally at first face value, you'll know what to perform. So when electrically safety testing a medical device, first you need to know what standard. You might be using a type test standard like 60601, or your recurrent testing type standard or code such as NFPA 99. You'll be carrying out a visual test. Now this is things like housing defects, chassis cracks, correct fuse ratings, etc. You need to establish, is it Class 1 or Class 2? What connections does it have? Does it have any exposed metal work? What types are they? So is there B, BF or CF? A patient monitor, for example, will have multiple functions with different types and applied parts. Now, classifications of applied parts is not actually relevant for NFPA 99. It does simplify the process. The applied part limits are the same. There's no different classification between whichever applied part you're testing. It's all identical. But if you're testing to 60601, then that's when the type of applied part becomes relevant. Sometimes you get asked what the difference is between a standard and a code. Well, a standard is a document that has all the technical procedures. It gives guidance for manufacturers and any equipment users. It contains requirements, but the compliance can be voluntary. A code such as NFPA 99, now that has been enacted into law by the regional or national authorities, so that then an engineer, a biomed, is legally obliged to comply to that code. It contains mandatory requirements that are obligatory. Now, adhering to standards is best practice, and adhering to that is good for quality management systems. But as you can see, the differences between these tests are quite minimal. They've got their equivalents. NFPA 99 is derived from 60601, and the methods are the same, but they have been simplified for the end user. So it makes things a little bit more efficient for the biomeds and engineers working in their workshops. And that does bring us on to NFPA 99. So NFPA 99 defines healthcare facilities, including hospitals, nursing homes, care facilities, clinics, medical and dental offices, and ambulatory healthcare centres. So there's a wide variation that needs to be considered of what a healthcare facility actually is. Now we will first find in the first few slides of the NFPA 99 codes is that there are system categories that need to be considered. Now it's up to the facility to define these categories through a risk assessment. So the first category, which has the highest risk, is where equipment failure for any duration is likely to cause serious injury or death. And a good example of this is an operating room. There's category 2. Now this is equipment failure is likely to cause minor injury. A good example of this is outpatient services. Category 3, so as we move lower through the risk values, then equipment failure is unlikely to significantly affect patient care, e.g. a dental room. And then category 4 is the lowest risk, and a good example of this is an exam room. Now it's important to note that the examples below may vary depending on the actual impact and risk. It's always up to the facility to categorise these types of areas. All areas in a facility must have a risk assessment. That is an absolute necessity. Categorisations do have an impact on safety testing. So for example, some electrical safety tests are actually omitted from category 3 and category 4 areas. So you don't need to perform specific tests in these particular areas. So there are categories are important to understand for electrical safety. So NFPA 99 is aligned with ES 60601. There are a lot of similarities. It's derived from that standard. But NFPA 99 is broad. It's the performance and safety criteria that refers to the healthcare facility in its entirety. It's not only the performance and safety of the equipment itself, it covers everything. So I'll give an example, closely related to electrical safety of the devices, but it's the ground bond and strain relief tests of the receptacles. So that's ensuring that the actual plugs, the extension leads, they have the correct polarity, and it's all part of the same procedure. Now in this webinar we're going to talk about the electrical safety tests specifically. So we are going to focus primarily on the equipment under test, whether it's fixed or portable. So each manufacturer typically produces a PM procedure for their equipment, and they will recommend intervals for testing. Now in previous revisions of NFPA 99, there were statements of 6 months in critical areas and at least every 12 months for general medical equipment. Now these statements seem to be phased out in most recent revisions, but the risk is still present. So best practice, at least every 12 months for testing medical devices. The risk there is still present, should be carried out regularly. Just ensures that the device is free from any hazards. Visual inspection. These help to identify any hazardous appliances in the healthcare facility pretty quickly. They form a critical part of the general safety inspections during the functional life of medical equipment. And this is because 70% of all faults are detected during this visual inspection. Now, it's not just biomeds that need to be aware of this, it's all staff that are using the equipment. They should be observant of the condition of the equipment they use, and that if any faults appear, that should prompt them to send it into the workshop for repair, and it should be removed from service altogether. Now, NFPA 99 doesn't state any formal or documented visual inspections by the individual, but a checklist is always handy to have in the workshop for you to follow, but it's general common sense. However, I've seen it in workshops where they've got a step-by-step guide of what needs to be looked out for, what you need to look out for. Now on our 2 Plus, so that's our automatic safety analyzer, we do have an option to add a visual test at the beginning of the test sequence, and then you have to manually check, pass or fail through those series of checks, which can be a useful prompt for any new users in the workshop. So what does a typical inspection include? So cases or chassis, looking for damage, looking for cracks or damaged plugs. These are all just sort of common sense faults that as experienced biomeds you'll know what to look out for straight away. However, this list could be useful to have somewhere in the facility. Also, one thing to mention is don't forget non-patient care related electrical equipment. Now this is stated in NFPA 99 that it must also be inspected by the staff or other personnel, and that's not just equipment that's owned by the facility, but also any patient-owned appliances which may be used in that patient care facility and may come into contact with a patient. It's not in this current slide, but the patient care facility is mentioned in NFPA 99, what that area is. Maybe I might add that into any future presentations. That's something that I've just realised is not on these slides. Okay, so we know that Class 1 equipment has a ground conductor that prevents harm to anyone. It's a proven safety measure for preventing electrical shock. So below the threshold of 500 milliohms in NFPA 99, and that is the threshold for failure. Any value measured below this is a pass. But if you think about it like this, if the body resistance is about 1,000 ohms, so 1 from the first line, I think 1 to 2 kilo ohms, even at the maximum allowable value of 0.5 ohms, that's still 2,000 times less leakage current that would flow to the human body, and it would go to the ground instead. We also measure that leakage current with the preceding tests. NFPA 99 has a few diagrams for the resistor meter, so this circuit is slightly different to how it's drawn in NFPA 99, but this is the correct schematic for measuring ground bond. It also has a few diagrams for the resistance meter in NFPA 99. So there's your resistance meter. This is one example of a circuit. This uses the 2-wire method, and it's simple but effective. NFPA 99 states there's various different schematics that can be used for measuring this. Leakage current, they can be broken down into ground, touch and patient lead leakage. The terminologies are always changing and people call them by different things, not just in between different countries, but even in the US, the terminologies can be used differently. So some people might call touch leakage, but it also might be enclosure leakage. They might call it chassis leakage, but effectively it's the same measurement that's being made. These terminologies are always changing in the standards and the codes, and it depends when you come into the field normally what terminology you'll be using. So the circuit is not mentioned in NFPA 99. There's no circuit like this really specified. This is from IEC 60601, and it does state that it should be close to the one found in that standard. And that just ensures that you've got the same frequency characteristics. So if you've got this circuit, then you'll be matching the frequency in the 60601. Now NFPA 99 does state that the frequency should closely match that of the one found in 60601. Now to measure these currents, you just need a meter which has the same frequency response characteristics of this body model. So without putting myself out of a job, you could of course make up one of these in the workshop with a voltmeter and a couple of basic components. But then you'd also need to make up adapters for simulating the fault conditions, such as open ground. Using a dedicated safety analyzer is what most workshops, in the Western world at least, would do, and those in our safe test range ensure you're getting the right measurements. So it's best practice to use safety analyzers, but of course the circuitry could be made up. So we've got ground leakage tests. These are not going to be as performed as often as your other leakage tests. They're only specified for fixed equipment in category 1 and category 2 spaces only, and that's before you install the equipment. Now to ensure that all the leakage current flows to the measurement circuit of the safety analyzer, this test is done before any grounds are connected. So you're performing this before you actually install the device. You're just testing the ground leakage before you've installed it. So leakage current is measured from the ground conductor of the power supply to the ground of the fixed appliance. And the current limit for this, although it's not on here, is 10 milliamps AC and DC. You're performing this test in both the on and off positions for the power switch of the device, and it's the same limit, 10 milliamps. It's a relatively straightforward test, and it's not going to be performed on many devices. Now, touch currents tests simulate a human body contacting different parts of the equipment. Now, it's any current that would flow from the person from the equipment chassis, or any accessible parts that are not intended for patient care, so patient leads. It applies to all portable equipment, and unlike 60601, there are no different fault conditions. They're just that the ground switch is open. Touch current tests simulate human body contacting these different parts of the equipment, and the measured leakage current values are just whether they're in acceptable limits, which is 500 microamps. Again, 2 measurements are taken, power switched in both the on and off positions. Now, if you use an automated safety analyzer like the 288, it will come up on screen. You'll carry out a touch leakage test, and it will say turn the device on, and then it will tell you to turn the device off between each prompt. So the test sequence for NFPA 99 is already automated in the 288. If the appliance is fixed to ground, then it's measured in situ with the ground open. The current must be measured using the power supply directly from a standard grounded system. This gives the highest possible leakage outcome, Now, we went over this in one of the previous slides for TN systems. Of course, we know that a good feature with the Rigel products is the auto detection of this TN standard system. This is where you could also use the recommendation of a grounded service, which is if you've got a non-TN system and you need to test that device in situ wherever you are, then you can briefly ground one side of the isolated power system for the leakage measurement. Now, this is in NFPA 9, they actually recommend this. It must be undertaken with a suitable adapter, which is plugged into an outlet on the system. They need to ensure that the neutral conductor is used and not what would be the live or hot conductor. And then once the test has been done, you just remove it after the measurement's been completed. And obviously this is hazardous, but it needs to be carried out by someone that knows what they're doing. So anyone in the biomed department who's experienced, it does allow them to perform something which is a good suggestion in NFPA 99, because those isolated systems is what we come across quite often in healthcare facilities. One thing that's also interested in NFPA 99 is there is a statement that has touch leakages when one power cord supplies the power to multiple devices. Now, comparing this to other standards I've looked at, it avoids quite a bit of confusion when testing things like stack systems. So in NFPA 99 it states that if a fault were to occur with the ground connection in the power cord, then the sum of all those currents from each individual device would flow to earth via any contact with the chassis. So it recommends that the touch current is just measured as a group, and the limit is 500 microamps as normal. There are also then suggested methods of lowering the sum leakage if you're getting higher than expected value. So if it's above that limit, you can then separate the devices grouping. But it's only required, obviously, if the values exceed that value. So it does save you a lot of time. If you've got a stack system, you measure it as a group. If it falls under that total leakage limit, it certainly saves you a bit of time. Now, one query I sometimes get about touch current tests or enclosure leakage tests is that what if there's no exposed conductive surface? It can be simulated by placing a 10 by 20 centimeter metal foil in contact with the exposed surface, and then that is considered the exposed surface of the appliance, and all appropriate tests shall be performed on that foil using either a crocodile clip or any type of thing that's going to contact that foil as you would test it normally. Now, if you've got a class 2 device that's fully enclosed, it might seem like a bit of a pointless test, but to go back to the one of the first few slides, I have to go back a bit. There it is. If you've got the foil placed on the enclosure, you're still going to have capacitance going to that enclosure, whether it's double insulated or not. And it's a good way to measure any capacitance, any capacitive coupling between the internal components and the enclosure. So it's a useful test for checking the leakages on anything that hasn't got exposed conductive parts. So a patient is any lead that has direct conductive contact with the patient and is often referred to as an applied part. This includes non-invasive and invasive connections. Now, the manufacturer will specify what is the applied part and what isn't. There'll also be classifications next to where the applied parts connect. This could be ECGs, could be pacemakers. There's all types of devices that it could be. Now, in NFPA 99, the patient leads are grouped together for testing. This wasn't always the case, so looking through some of the previous versions of NFPA 99, it does state that individual applied parts to ground must be measured. However, in the last few editions of NFPA 99, including this one, 2021, patient leads are always grouped together for testing. So saving yourself some time there. That's what NFPA 99 recommends. The leakage limits are total leakage limits. So 100 microamps for ground wire closed and 500 microamps for ground wire open. So it's performing 2 tests with 2 different fault conditions. So here's just for some clarity on the tests, their limits and single fault conditions. They're there clearly in the code, but it might be useful for you to have. So this is the 2021 limits. Print a copy, stick it on the wall. Good for a quick point of reference if you need it, especially if you're using a manual tester and you've got a new biomed that's not entirely sure of the limits and fault conditions. This gives you a bit of an idea of how it's performed. So what are the best practices? It's the facility's responsibility to identify which equipment requires regular checks. Each device must be tested at acceptance in accordance with NFPA 99 and during any maintenance that may affect the electrical integrity. Best practice, every time you open up a unit and you make any changes, you just carry out a test. But there are also recommendations on the minimum periods for safety checks whilst in service, and we say that at least every 12 months. However, the responsibility for the duration of retention of test records always falls on the healthcare facility's record policy. And I pulled this directly out of the code, NFPA 99 code. It does fall on the healthcare facility's record policy. Now, this is where alternative maintenance procedures, the periodic testing can vary widely once you've got evidence of safety and reliability of the devices that are in your workshop. So periodic testing may vary to this, as long as you've got evidence that proves that and you've got it in your risk management policy. Also appreciate that secondary ground connections and isolated systems will lead to invalid measurements. Now our safety analyzer do have these prompts, so if that does show up, then you know you need to either disconnect that device from the secondary earth, or you need to move the safety analyzer and the device to a TN system. NFPA 99 states the minimum documentation that's required for routine checks. Each record must at least define these things. Now, you might actually record more than this, but this is the bare minimum. What was tested, that's the unique identification of the equipment, the date it was tested, and whether it passed or failed. Test protocols should be developed to ensure consistency for each electrical safety check and record. So the aim of electrical safety in NFPA 99, and that of all electrical safety standards, we know that it's to limit leakage currents that can cause injury to a patient or user. So it's always best practice to keep that risk of electrocution to a minimum, regardless of what the minimum requirements are in the standard or code. It's also worth looking at the OEMs, so the original equipment manufacturer service manuals for their guidance. That's what it states here at the bottom. Service manuals may specify specific checks, but just remember that the NFPA 99 code is law and it must be followed first and foremost when it comes to electrical safety. So to be more thorough, it's always worth contacting the manufacturer to see what they recommend in terms of testing. So electrical safety analyzers. The NFPA 99 handbook clearly states about the use of dedicated electrical safety analyzers. So how do you choose? Well, an analyzer must simply produce the results you require accurately and repeatedly. They must have a body model similar to NCME 60601 and traceability of measurement results. So the first 3 points there, If you're picking from a reputable manufacturer of biomedical test equipment, then you only really need to worry about user preference. So test convenience, including test duration, user interface, time efficiency. It could be the support you get from the manufacturer. It's all, at the end of the day, it's ultimately user preference. So grab a demo from one of the manufacturers, from the representative, try it out, see what you think, and then that gives you an idea of which analyzer you prefer and want to implement in your organisation. What you may find is that an analyzer is specified in a manual. Rigel has their own safety analyzers recommended in specific service manuals, but realistically you don't have to use that safety analyzer. You can use any safety analyzer you want. It's just what's recommended. It's all about using an equivalent tester if you prefer that unit. So user preference is the overriding factor, as long as it's from a reputable manufacturer. A quick overview of ultrasound testing, because we do sometimes get queries on this. How do you perform it? Ultimately, you should contact the manufacturer to ask them about the process of testing their ultrasound probes. But there is guidance that we provide for testing ultrasound. We do it in two parts. So we test the ultrasound alone without the probes, and then we test the probes alone. So in the first part, connect a Rigel 288 or a safety analyzer without the probes, and we'll just run an NFPA 99 test as you normally would. We select a semi-automatic mode and run a simple test. Now, the reason for this is that the ultrasound devices are potentially power up and power down sensitive, as they're often PC based. So doing an automatic test won't allow time for those load up and shut down times. In the second part, we test the probes alone. So the ultrasound is connected to the analyzer and powered on. All the probes are placed into a plexiglass container filled with half a litre of saline solution, and you can place up to 3 probes in the saline together at once. We're doing a 30-second test. So if we think about this from the application of ultrasound in the setting, a clinician uses ultrasound gel. That gel is water-based and it's conductive, and it's designed to remove air, which is an insulator, so that ultrasound waves can travel easily between the body and the probe. Now, if you imagine that the insulated casing of an ultrasound probe became cracked, then gel could ingress into that circuit where you've got the potential of current flowing to the patient. Now, what we're doing here is we're replicating that using saline. It's replicating that condition, and it's very effective. It's important that we don't fully immerse the probes to a point where really we just think that the patient is going to be coming into contact. It's all about application and how it is in the real life setting. The duration of the test is 30 seconds, and that just ensures that the saline gets a good contact between the circuitry, electrode within the probe, and the patient leads. And that's just what we recommend. But it's always best to just contact the manufacturer when it comes to these types of tests. Okay, that's the end of the presentation part of this webinar. I'll just go through some of your questions, and while that's ongoing, the demo from James will be carried out now, so I'll pass you over. Once that's done, at the end of this whole webinar, I will go through some of your queries and answer them as best as I can. Any questions in the chat box or the question box below.
Hi everyone, my name is James Durrance and I'm the Business Development Manager here at Rigel Medical. And today we're going to be using the Rigel Medical 288 Plus Electrical Safety Analyzer and performing an NFPA 99 manual and automatic test on the Philips 3-lead patient monitor. Now before we run any tests, we need to hook up the device. So first you're going to take your power cord and you're going to plug that into the back of the device, ensuring that the two white lines connect with each other. Next, you're going to take your applied parts box. There's a little red dot on the applied parts connector that's going to face forward, similar to the white lines on the power box. Next, you're going to take your earth bond test probe, plug it into the black connector on the back of the device. Now that the earth bond test probe is connected, you're going to take the probe itself and connect it to the back of the Philips monitor at the ground lug. Now you're going to take your applied parts box and you're going to start connecting your ECG leads. I have 3 lead ECG, so I'm going to connect the right arm, the left arm, and then finally the left leg. Now that those leads are attached, you are going to connect the device under test power cord to the front panel of the 288 Plus. Once it's all connected, you can turn the 288 unit on and notice the LCD screen will light up. So now I'm going to run a quick earth bond test. You're going to go to the menu, F4, go down to manual mode, and it's going to be the first one on the list, earth bond. Select F4 to select the test, and the green button to start the test. And once the check mark is displayed, that means the device has passed the test. So now that the device is powered on, you can select F4 to select your test mode. We're going to do manual. And today we're doing NFPA, so I'm going to scroll down to NFPA, open up that menu. And the first test we're going to run is earth leakage. Select F4 to select the test. Now that everything is hooked up, hit the green button to start the test. Now once the test is complete, you will need to note that the results are displayed as 47 microamps, and the check mark on the side is displayed, meaning it has passed the test. Now we can hit F4 again to open up the menu, go down to manual, and select NFPA again. And now we are going to run the chassis leakage test. Select F4 to select the test, and the green button to start the test. And again, with this test, you'll need to record your values. This came in at 47 microamps, and the check mark will also display, meaning that the device has passed the test. Now we're going to start our next test. Select F4 to open up the menu, go down to manual, and we are still testing for NFPA standards. So go down to NFPA, and this time we are testing patient leakage. Scroll down to patient leakage and select F4 to select your test, and the green button to start your test. Now you'll notice a few things about this. On the LCD screen, you have an AC warning. This is signaling to you that you should not touch any applied parts. These are live connections. And it is searching and receiving less than 4 microamps. And every time a check mark pops up, that is one lead passing a test. After it has cycled through all of the leads, the check mark will remain on the screen, signaling to you that the device has passed the test as a whole. Now we can select F4 to open up the menu, go down to manual mode, and this time we are going to scroll down to lead leakage, select F4, and hit the green button to run the test. And right now we're getting a reading of less than 4 microamps. And when the check mark pops up on the screen, that means the device has passed the test. Now you can create a specific test code for your auto test. select F4, and scroll down to Setup. And then you're going to select Test Codes with F4. Now to create a new code, you're going to hit F1, and to edit that code, you'll hit F4. At the top, you can change the name of the code. Select F4, and you have up to 4 characters to make it whatever you'd like it to be. After I've created that, I'm going to scroll down and make it an automatic test and hit F1 to get your specific applied parts. Select F2, and for me, I'm testing an ECG right now, so I'm going to make it an ECG applied part by scrolling down and selecting F4 over ECG. And I only have a 3 lead right now, so I'm going to select 3, and you can do up to 10 leads. Select F4 to save your changes. Once you're back to this screen, select F4 again, and now you can get your actual test sequences. Select F1 to create a test sequence. This will be the standard that you're choosing to test. Right now we are doing NFPA, and my device is a class 1, so I'm going to choose NFPA class 1 and select F4 to choose that test sequence. F4 to save, and when you select F3, it's going to ask you if you want to save your changes. Select F4 to save those changes. Now that we've developed our test code, we can use it in an auto test. So you're going to select F4, auto mode, and your asset ID can be whatever you'd like it to be. I'm just putting in a random number. For test code, we are going to enter that 4-character code that we have already developed, and that will autofill all of the information we've already developed. I'm just double checking here to make sure that it's set up for my 3 ECG lead. Everything is correct. It's giving you the warning of, are you sure you want to run the test? You hit the green button and it starts cycling through the tests. Now that the monitor is off, I can run the next test. And now I can turn the monitor back on to continue on the test. And as this auto test is running, it is going step by step through every NFPA test that we have already done in manual mode and automatically saving the results in the device. All the user has to do is turn their device under test on and off when prompted and hit the green button when prompted. Once you get to this screen, that means the test is complete and you can input anything you want. It's passed the test, so I put that it is passed the test and select F4 to save the data. Now that the test is complete, you can go into the unit and view the test results. So you're going to select F4, go down to View Data, and select F4. And it's always going to be at the bottom of the list. And from here, you can select that specific data set, see that it has passed the test, and if you hit F4, you can do a few things with it. You can print your results, you can view the sequence, you can view the results itself. Right now I'm viewing it, and it'll show every test step by step and the results of that. And then you can print the results if you have a printer hooked up to it as well.